Welcome to Differential Equations and Linear Algebra. Before we get started in section 1.1, we're going to look just very briefly at an introduction to these two topics that we're going to be spending the semester studying. So a differential equation, often abbreviated a DE, is basically just what it sounds like. It's an equation involving one or more derivatives of an unknown function. So we have a few examples down here. So things that should look relatively familiar. So dy dt equals 100 minus y squared with an unknown function y of t. You can have dq dt, unknown function q of x. You can have something that's a little less conventional that we haven't talked about in our typical calculus, the idea of having multiple derivatives in the same equation as each other. Here we have an unknown function a of t. We'll be working with many different types of differential equations throughout different chapters in this course, and we'll look at many different ways of solving those types of differential equations. We'll also be spending a large portion of the semester studying linear algebra. Linear algebra is considered the threshold of higher theoretical mathematics. So it's where we start making the transition from more algebraic and computational mathematics into more theoretical and concept-based mathematics. It's primarily the study of systems of linear equations, hence the name linear algebra, modeled with matrices. We'll look more at those later on. And linear algebra, the reason we study it at the same time as differential equations is because it can be a valuable tool for solving systems of differential equations. So for example, here we have x prime equals 3x plus 4y and y prime equals negative 5x plus y. Being able to solve a system with multiple unknown derivatives is going to be a valuable tool to us that we'll look at later on in the semester. So our plan and kind of the guide map for this course, we're going to study differential equations as far as we can without considering systems. Then we're going to reach kind of a wall where we need to stop talking about differential equations. We're going to learn linear algebra. And once we have the tools of linear algebra at our disposal, we're going to return to differential equations and start looking at systems of differential equations and start applying those linear algebra concepts now that we have them. So that's where we're headed this semester. But as with any journey, we have to start at the beginning. So let's go ahead and start with section 1.1. Differential equations everywhere. So differential equations come up in many different contexts, many different scenarios. We're only looking at a couple briefly here, and we will see some examples with these in this section and in future sections as well. So some cases where differential equations arise. First primary example would be the idea of position, velocity, and acceleration. So you learn in calculus that the derivative of the position of an object is given by the velocity. The derivative of the velocity is the acceleration. We can establish those using functional notation. So we have y of t is the position of an object, y prime of t is velocity, y double prime of t, or derivative of velocity, is acceleration of an object at time t. This gives us opportunities to set up equations with derivatives because, of course, they are taking derivatives as we go down this process. So consider an object moving through space subject only to gravitational force. We know the acceleration of that object, which is often referred to just as g when it's gravitational acceleration, can be written as 9.81 meters per second squared or 32 feet per second squared. If we were to take this gravity acceleration formula and integrate it twice, we would get this formula for y of t, the original position of an object subject to gravity. And we've substituted out the specific number for gravity with g, just so that we could transpose this into either meters or feet, depending on the context. So we have this general formula in terms of t. So 1/2 gt squared plus ct plus d, where c and t are constants. We can use this to solve problems involving gravitational force, position, velocity, and acceleration. So let's look at an example of that. So I've got a little bit of setup here for us. So a boy, 2 meters tall, shoots a rocket straight up at 10 meters per second. What is the highest point reached by the rocket, and when does it hit the ground? So we've got a couple questions here. What is the highest point that the rocket reaches, and when does it hit the ground? So we're looking to find what that highest point is and the time at which it hits the ground again. So we have a couple things to set up here. So I've set up a couple notes. We're going to let y equals 0, that initial value, that initial position of the rocket, be where the motion begins. So it's being shot off. The boy is 2 meters tall, so the rocket's being shot off, presumably at a 2-meter height. So if we assume that's true, then 2 meters off the ground is where our initial y equals 0 value is going to be. That'll come into play towards the end when we get our formulas set up. And then the other thing is we're assuming a downward positive orientation due to gravity. So gravity is always pushing everything down towards the surface. So when we're setting up positive versus negative, we're assuming that everything going down is moving in a positive direction. Everything going up is moving negatively because it's moving against the force of gravity. All right, so let's get some setup in here. So since y of 0 equals 0, so our initial position at time 0 is 0, right? It hasn't been launched yet. In our equation back here, y of 0 would be 0 plus 0 plus d. So that just gives us d is 0. Then we know y prime of 0, the rocket is being shot straight up at 10 meters per second. So the velocity initially is 10 meters per second, but remember, it's being shot against gravity, so it's going to be negative 10 meters per second. So y prime of t, if this is y prime, we would bring down the 2 and just get gt plus c. We would substitute in 0, that's equal to negative 10. That gives us c is negative 10. Thus, if we know c and d, we know this equation. So y of t is 1/2 gt squared, again where g is that force of gravity, minus 10t, and then plus 0 because the d is there, so we don't need to write that. So this is the formula that we're going to be working with. Now, in order to find the highest point reached by the rocket, that highest point is going to occur at the top of this arc, right? This parabolic arc that occurs. That point happens when our velocity has stopped going this way and has started going this way. At that precise moment at the top of the curve, that is when the velocity is 0. So the highest point is when velocity is 0. So if we take the derivative, so that's the velocity, that was gt minus 10. Set that equal to 0. We're going to get t to be 10 over g. This would be the time at which it has reached its highest point, but it wants to know what is the highest point reached by the rocket. So we need to put it back into the position function to find that answer. So we're going to sub into y of t. So we get y of 10 over g. So that's 1/2 g times 10 over g squared minus 10 times 10 over g, which when you combine all of that together, simplify, you get negative 50 over g. So the highest point, this is the position that we get, negative 50 over g. Now we have to think about this again with these notes in mind, with that context in mind. Because this is negative, what it really means is it's that far off of the ground. But remember that it didn't start at ground level, it started 2 meters off the ground. So this distance of 50 over g is the distance from here. If we want the highest point, we want to go ahead and add those 2 meters back into that final answer. So the highest point is 50 over g plus 2 meters. Above the ground. And because we're working with meters, we can go ahead and approximate using the meter value, and it's about 7.1 meters. So it's a little more than 7 meters off the ground is that highest point. Okay, so a little more than 5 meters above where it started. And then it's asking, when does it hit the ground? So when it hits the ground, that is when its output, its position, is 2 meters past where it started. So we're going to say, so hits the ground when y of t equals 2. Remember, downward positive, so that is a positive 2 because it's closer to the ground. So we're going to get 1/2 gt squared minus 10t. Set that equal to 2. If you solve this out for t, it doesn't work very nicely. It's not something that we can factor. So we need to involve something like the quadratic formula or completing the square, one of those algebraic techniques. But we do end up getting 10 over g plus the square root of 400 plus 16g over 2g seconds. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . we would normally incur like a plus or minus case, but the minus case would actually make the time negative. And so in the context, that doesn't really do anything for us. This is approximately, if you substitute in that meter value for the gravity, then that's going to be approximately 2.22 seconds that it takes for the rocket to reach the ground after it has been launched. All right. Another context that we're going to look at a little more later on in the chapter is Newton's law of cooling. Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the temperature difference between the object and its surrounding medium. So the rate of change of the temperature is proportional to the temperature difference between the object and its surrounding medium. So basically, the bigger the temperature difference between the object and the room that it's in, the faster the object will cool, the faster that rate of change will be. So if you take something right out of the oven and you set it on the counter, right, it is going to cool because the difference in temperature is pretty large. If you took an object out of the oven and immediately put it into the freezer, that object is going to cool faster because the difference in temperature is greater between the freezer and the object. Whereas if you took something from like the refrigerator and put it into the freezer, the temperature difference is there, but it's not nearly as big. It's going to take that object a lot longer to cool to that lower temperature than it would if it was a lot hotter. So you can visualize this on a graph like this. So see, as the object's temperature decreases here, that's purple. T sub m, that's the temperature of the surrounding medium, stays the same. As time passes, the difference between these temperatures is shrinking. But notice it's getting smaller very quickly at first, and then it starts leveling off a lot more as we go further down because the temperature difference is a lot smaller, so it cools a lot slower. Using these variables, there is a differential equation that governs this relationship, and that is dt, so derivative of temperature with respect to time, equals negative k times the quantity T of t minus T sub m. And again, this is where k is what we call the proportionality constant, greater than 0. Notice there's always going to be a negative in the front because the temperature is shrinking. And then T of t, that is the object's temperature, and then T sub m is the temperature of the medium or the room that it is in. We will be looking in a future section at the actual solutions to this differential equation, how we can find those solutions, and then how we can apply those to solving problems. But that will come in a future section. So that's the end of section 1.1. So just our introduction into a little bit of application of differential equations. Now we need to look at some basic terminology in section 2. So a differential equation that can be written of the following form. So g of x, y, y prime, y double prime, triple prime, all the way up to the nth derivative equals 0 is called nth order. So a differential equation is nth order. Basically, the order of a differential equation is determined by the highest derivative in that equation. So if an equation has a fifth derivative, it's fifth order. If an equation has a first, second, third, fourth, fifth, sixth, and seventh derivative, it's seventh order because that's the highest derivative in the equation. A differential equation of this form, so you've got a coefficient function here on the nth derivative, another function on the n-1 derivative, etc., 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 is called linear. And we will be working a lot with linear differential equations. So, for example, for part A, we have x squared y triple prime plus 3y double prime equals sine of x. This would be third order because the highest derivative in the equation is the third derivative. And all of the derivatives are raised only to single power terms. So we're not like squaring or cubing or doing any of that to the derivatives. So it is linear in nature. So this would be considered third order linear. Something like part B, so y double prime plus 3x, y prime cubed minus y equals 1 plus 3x. The order would be 2, but because one of the derivatives is raised to another power, that makes it nonlinear. So this would be second order nonlinear. Then we have the Newton's law of cooling formula from section 1. The highest derivative in it is just this first derivative here, dt dt. So it is just first order, and that's the only derivative, and it is not raised to any power, so it is linear. So this one is first order linear. So let's start with a more specific example that we might be a little more familiar with the concept of. So here we have y double prime equals the square root of x. So this is a differential equation. This is second order linear. So the highest derivative in it is the second derivative, and it is linear. If we want to solve this differential equation, that's basically just asking us to solve for the function y that satisfies this relationship. Now, when it's set up in this format where the derivative is directly equal to a function of x only, this is what we're used to dealing with in calculus. So these are things that we can solve directly using the tools we already have. And we do that just by integrating or by taking the antiderivative. So on the left-hand side, if we take the antiderivative, we get y prime. On the right-hand side, remember the square root of x is x to the 1/2 power. So to take the antiderivative of that, that's going to be 2/3 x to the 3/2 power plus c. Get that constant of integration, that arbitrary constant. And then to find y, we take one more antiderivative. So we're going to add 1 to the power, divide by that same number, incorporate that with the 2/3. We get 4/15 x to the 5/2 plus the previous constant picks up an x, and we get a new constant of integration. So that'll be plus d. So this would be our solution to the differential equation. So anything that has this general form would be a valid solution to that relationship. So now, of course, the solution above here has two unknown values in it, as it is when you take indefinite integrals or just take general antiderivatives. So this is what we call the general solution to the differential equation. If we want to solve for those constants and figure out what those specific values would be, we have to be given initial conditions. Now, if we do have initial conditions, a differential equation together with those initial conditions form what we call an initial value problem, abbreviated IVP. An IVP can be solved for what we call a particular solution with all constants determined. So if we do not have any initial conditions, we cannot solve for those arbitrary constants. That's what we call the general solution, right? Because there could be any number of constants that satisfy this relationship. But if we do have an initial condition, we can find one specific or particular solution that will solve that equation. For example, if we look at the top of the next page, we have the same problem, but given two initial conditions. So we already know the general solution to this. So it was y equals 4/15 x to the 5/2 plus cx plus d. Using these initial conditions, we can get more specific. We know y of 0 is 7, y prime of 0 is 1. So let's see. Well, let's start with y prime of 0. So y prime, if we go back up here, that was this. That was 2/3 x to the 3/2 plus c. So this is 2/3 0 to the 3/2 plus c equals 1. So that just gives us c equals 1. And y of 0, so using this function y, so that's 4/15 times 0 to the 5/2 plus 1 now times 0 plus d equals 7. So we get d equals 7. It doesn't always happen that way, that the number is just whatever it's equal to. There might be other solving in here. It might not always be 0. So there's different situations that can arise, but that's what we get in this case. So our particular solution, the one that solves this differential equation and satisfies both of these conditions, is y equals 4/15 x to the 5/2 plus x plus 7. So this function is a solution to this specific set of circumstances. So again, this differential equation subject to those specific constraints. Looking at a slightly different example, here they give us the general form of a solution, and they ask us to basically kind of fill in the gaps. So find all values of r such that y of x equals e to the rx solves this differential equation. So we have y, we need y prime, we need y double prime. So let's get those. So y is e to the rx. Y prime, the derivative of that, will be e to the rx again times r because of the chain rule. And then y double prime, we'll do the same thing again, and we'll pick up an extra factor of r. So given all of these derivatives, let's just substitute in to the differential equation. So we get y double prime minus 8y prime plus 16y equals 0. And now we need to find all values of r that make this true. Notice there is that common factor of e to the rx in everything, so let's go ahead and just factor it out. We'll be left with r squared minus 8r plus 16 all equals 0. This object within the parentheses is factorable, so it gives us r minus 4 quantity squared. So we have e to the rx times r minus 4 squared equals 0. So we would be able to split this. Now the r minus 4 squared, of course, that just gives us a solution of r is 4, right? That's what makes that 0. This one, however, there are no values in an exponential function like this that can turn it into a 0. If you pick 0, you get e to the 0, which is 1. If you pick a negative, it just becomes a fraction, but still positive. And if you pick positive, it just grows infinitely large. So e to the rx set equal to 0 produces no solutions. So no solutions. So that means the only value of r that makes this function satisfy this differential equation is 4. So our solution, y of x equals e to the 4x. That is the only function that will satisfy, of this form, that will satisfy that differential equation. All right, so that brings us to the end of section 1.2. That is our introduction into the concept of differential equations. In the upcoming sections, we will be looking at more specific types of differential equations and how we can solve those.